Hello friends, grab your coffee, grab your cookie, and maybe keep both away from any grinding wheels, because today we are talking about iron dust. Yes, the dust that looks like ordinary dark powder but can damage equipment, cause respiratory irritation, and under the right conditions, behave like a combustible metal dust defined under NFPA 484. My name is Michael Klepik, and for 15 years I have been designing dust collection systems for foundries, metal shops, machining centers, welding lines, and steel processing plants. Let me explain why iron dust is not as simple as it looks. What iron dust really is. Technical description. Iron dust forms during grinding, cutting, drilling, polishing, casting, and surface preparation of iron and steel parts. Technically, first, particle sizes typically range from 1 micron to 200 microns. Second, the most airborne fraction is from 1 to 20 microns. Third, bulk density is high, generally from 4,000 to 7,000 kilograms per cubic meter. Fourth, dust often contains iron oxides such as magnetite or hematite. Fifth, freshly generated particles can oxidize rapidly, increasing heat and reactivity. Iron dust is heavy but highly reactive. Where iron dust is common in industry, you will find iron dust in first, grinding and polishing of steel and cast iron. Second, foundry shakeout, casting, cleaning, and fettling lines. Third, machining centers, CNC operations, and abrasive cutting. Fourth, welding stations with grinding and prep work. Fifth, shot blasting and surface finishing operations. Sixth, metal recycling and shredding plants. Anywhere iron parts are shaped or cleaned, dust appears. Hazard summary. Why iron dust is dangerous. Iron dust presents several major hazards. First, fresh iron dust can oxidize and generate heat. Second, fine iron particles can ignite under certain conditions. Third, iron dust can cause mechanical irritation to the lungs. Fourth, magnetic dust accumulates inside motors, bearings, and electronics. Fifth, iron oxide dust reduces visibility and causes housekeeping problems. Sixth, dust buildup increases slip hazards and contaminates lubricants. Iron dust is physically heavy but chemically active. Combustibility and NFPA 484. Compliance. Most people assume iron cannot burn, but fine iron dust can burn, and NFPA 484 recognizes iron as a potentially combustible metal when finely divided. From a compliance perspective, first, fine particles with high surface area ignite more easily. Second, iron oxidation produces significant heat. Third, dust clouds can ignite from welding arcs or grinding sparks. Fourth, accumulated layers increase explosion severity. Fifth, OSHA requires hazard recognition under the General Duty Clause. Iron dust is not as explosive as aluminum or magnesium, but it is still a combustible metal dust. Physical behavior of iron dust in airflow. From an engineering standpoint, iron dust behaves in unique ways. First, it is heavy and settles quickly in low-velocity ducts. Second, extremely fine fractions remain airborne and travel far. Third, magnetic particles stick to steel ductwork and fans. Fourth, abrasive particles erode duct elbows and collector inlets. Fifth, iron oxides can pack tightly on filter surfaces, increasing pressure drop. Because iron dust is dense, I designed duct velocities from 4,500 to 6,000 feet per minute. Filtration equipment that works best for fine iron dust. A FOEH and cartridge collector is effective. First, high-efficiency media captures very small metallic particles. Second, conductive and anti-static filters reduce ignition risk. Third, strong pulse cleaning controls dense iron oxide buildup. For heavy grinding and foundry dust, a Baghouse blizzard is ideal. First, large chambers tolerate heavy abrasive loads. Second, filter bags withstand impact from coarse particles. Third, rugged construction handles foundry conditions. Abrasion control iron dust requires, first, abrasion-resistant duct elbows. Second, ceramic liners for high-impact zones. Third, inlet baffles to shield filters. Explosion protection and grounding requirements, even though iron is less reactive than aluminum. First, explosion vents are required when dust is combustible. Second, duct isolation valves prevent deflagration travel. Third, all metal ducts must be fully bonded and grounded. Fourth, anti-static filter media reduce spark hazards. Fifth, hot surfaces must be controlled to avoid ignition. Compliance with NFPA 484 is essential when dealing with metallic dust. Capture hood design for iron dust processes. Effective capture significantly reduces airborne hazards. I use, first, enclosed grinding and cutting hoods. Second, multi-point extraction along polishing benches. Third, downdraft tables for surface prep operations. Fourth, capture at CNC tool change and machining points. Fifth, high-velocity extraction at foundry shakeout stations. Good capture prevents heavy particles from settling inside duct systems. Iron dust may look simple. After all, it is just iron, but fine particles of iron behave like a reactive, abrasive, and partially combustible metallic dust. They damage equipment, irritate lungs, and under NFPA 484 conditions, can ignite or contribute to large dust events. With strong airflow, high-efficiency filtration, abrasion-resistant design, and full OSHA and NFPA compliance, we can control iron dust safely and reliably. I am Michael Klepik. Protect your lungs, protect your equipment, and remember, iron belongs in your steel parts, not floating through your facility. See you in the next video.